You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Professor Jason Wright. Jason Wright is a professor of astronomy and astrophysics at Penn State and a member of the Center for Exoplanets and Habitable Worlds. He studies stars, their atmospheres, their activity and their planets, whilst also working on SETI. He is a project scientist for NEAD, a PI of the Nexus for Exoplanet System Science, a co-PI of the Miniature Exoplanet Radial Velocity Array, and a member of the Habitable Zone Planet Finder team. You can learn more about his research on his blog. There's a link in the description, or by following him on Twitter at @astro_Wright.
Jason Wright, welcome to the program.
Thanks for having me.
Now, Jason, you recently authored, as in it came out several days ago, a paper on Dyson Spheres, which have long been a subject within astrobiology, very early one, going back to Olaf Stapleton in the 1930s, that you could encase a star in a shell and harvest 100% of its energy. Since that time, people have said, well, this is probably not feasible in that form. Do you think an actual monolithic Dyson Sphere is possible?
Certainly not. And Freeman Dyson did not either, as it turns out. It was at the dawn of modern SETI in 1960, right around the time that Frank Drake was starting Project Ozma to look through the skies for radio signals, that Freeman Dyson, inspired by Olaf Stapleton's novel, wrote a paper saying that if you had a technological species that was very energy hungry, that it might create what he called an artificial biosphere around the star. And his rationale was just that that's the most energy that any species could ever collect in a stellar system. And he pointed out that that would have a lot of observational consequences that would be observable. And in the letters to the editor to the journal, people objected that if you were to actually build a shell, like a sphere, around a star as some sort of monolithic object, like in Star Trek or something, that it would be unstable for a lot of reasons. And he responded to those letters by saying, yes, he knew, thank you very much, but that he really had in mind more of a swarm of material and not some kind of single monolithic object.
Now, as a technosignature, just as a quick question, as a technosignature, if you had a swarm that was emitting an infrared versus a shell in infrared, could you tell the difference?
In some ways, what Freeman Dyson had in mind was that the energy of the star, even if it's being used by the species, no matter how efficient they are, they can't destroy the energy. And mass energy is always conserved. And so when they were done using the energy, when they had extracted all of the useful work from it, they would necessarily have to dispose of it as heat. Just like your computer might take power from the wall, it does lots of useful work, it does all the things that it does, and then it heats up and it gets rid of the energy and it has to go draw some more. And so that's true for any material that orbits a star. It's true for planets, it's true for debris disks, it's true for dust, it's true for a monolithic shell, and it's true for a swarm of objects as well. So in that sense, it doesn't really make any difference how the material is distributed. Now, there's another way to detect these things, though, which is that if you have a significant amount of material around a star, it'll sometimes pass between the star and Earth, or maybe it'll be constantly passing between the star and Earth, and blocking the star's light. And that tells you a lot about the structure of the material. If it were a solid object, it would, of course, just block all of the star's light. But if it's a swarm, you might see what Freeman Dyson called chinks in the armor, as you would get more or less light filtering through the swarm.
Now, this evokes Luke Arnold's paper that you could actually signal,
exactly,
using a louver or a very unnatural shape. Say you put up a big, huge mylar sheet that was square shaped. You could actually see that in the light curve of a star as it passed in front of the star. So that's a completely separate way from infrared to look for a technosignature, right?
Yeah, that's right. Luke Arnold proposed this just as the Kepler Space Telescope was going up and before it had sent down any data. he wasn't thinking so much of a Dyson sphere collecting lots of the energy, but as you said, as a beacon, something that might be deliberately set up to get our attention. So, I mean, such a thing would have to be the size of a planet, because it takes planet-sized things to block enough light for us to notice around nearby stars. But that's exactly right. When a planet passes between a star and Earth, we see a very characteristic dip in the star's brightness. It gets 1 or maybe 1/10% dimmer as the planet goes in front, and then it gets brighter again. But if that thing passing in front were a triangle or some other strange shape, then the pattern of the light getting dimmer and brighter will change. And so he suggested that we look for things that look a bit like planets, but imply the wrong shape, not a circular aspect, or perhaps things in unnatural orbits, like things sharing an orbit, maybe prime numbers of objects going by in a pattern or something like that. This is a very clever idea. And an extension of Freeman Dyson's idea of a Dyson swarm.
Now you could, you mentioned prime numbers going by. You could, in theory, encode some kind of data in such a visual cue, right?
Yes, it would be very low baud, but you could do it. So Luke Arnold imagined, as you say, louvers, that you might be able to actually actuate panels or something on this planet-sized object. And so based on the aspect it presented, you would get a different amount of dimming of the star, and that would convey information. So you could flash prime numbers, you could flash Morse code, but it would be very, very slow. You would get a few bits per hour or per orbit or something like that. So it would necessarily probably have to be a beacon, just a simple "we are here" message. And if you wanted to convey anything of substance, you'd have to have some sort of sub-channel. Maybe you would also be broadcasting in the radio. So the giant louvers or something are there to get your attention and let you know there's something else there to find.
Let's talk about costs, because it seems to me that if you were going to announce your presence to the rest of the galaxy, it doesn't really make sense to build a gigantic omnidirectional radio beacon blasting out energy at multiple wavelengths, or even just at 1420, the hydrogen line. Rather, this visual method, which seems to me would be a lot more feasible long term and a lot cheaper of a way to, if your aim is just to say we're here, it seems to me that it's a much more feasible way to do it, right?
Yeah, that's exactly Luke Arnold's argument, that if you want to send out a lot of energy to get detected, you have to have that energy to send out. But stars are already doing that for free. They're already shining that out. In fact, we've already noticed the star. And so you only have to expend energy enough to modulate that signal. And the nice thing about an orbiting structure is that if you set it up right, it should probably be stable for a long time. That is, it'll just keep orbiting the star over and over and over. And it might even outlast, the species that built it or something like that. Now, there are some issues with building something so large that can't maintain itself. You have to worry about radiation pressure, you have to worry about its attitude control, but in principle it could be very long-lived. And so, right, the main cost is in actually constructing it in the first place. And then after that, it just transmits essentially for free for a very long time.
Now, you would also have to position it to make sure that it transits in the line of sight of something. So if you're an alien civilization and you look and you see Earth, and you're like, well, we have this exoplanet with really weird oxygen levels and methane levels. There's probably something there. So we're going to build, just in case civilization ever shows up, we're going to build this big louver and make it transit within their line of sight. But this isn't really something that you could do with the entire galaxy. You could maybe align it with the galactic plane or something like that and just hope someone saw it. But you couldn't really send out in all directions this kind of a message. It's directional.
Well, each individual one is directional, but if it's pretty close to the star, it might cover a few % of the sky. And if you set up, 20 of them, then you would have an omnidirectional transmitter. You would just need, one for each slice of the sky that you wanted to transmit to.
So you could, in theory, make an array.
Yeah, you would have essentially a swarm of these things. And, it might need only be 10 or 20 of them or something if they're large enough. That's right.
Now, going further, now we're getting into Dyson Sphere territory again, because then once you start putting up a number of these things, you're basically building a Dyson Swarm.
That's right.
could they be multiple use? For example, could you build a louver that on one side is signaling and sending out a message for anyone studying SETI, but dual use, it's also collecting energy. So you could probably make your SETI experiment work for you in other ways other than just simply announcing, right?
Yeah, that's right. And in fact, if you want to collect a lot of energy, then you need to have a lot of surface area. And while you could do it with a large number of small collectors, you could also lash them all together. And you might think of it the other way, that the beacon comes for free. Or even imagine that if you're just trying to get a lot of energy, you might not even be intentionally sending out a beacon. It could just be that that's the sort of thing you end up building over a very long time as you put more and more solar panels, let's say, in space in one spot to do whatever it is you do with all of that energy. I'll point out that you not only need large collecting areas if you're going to use the energy of the star for computation or whatever it is that you do. You also need to have radiating surfaces to radiate that energy away, just like you need radiator fins on something that generates a lot of energy to dump the heat. And so you can't get away from having very big panels, even if you're not using the starlight. So even if you have some other way of getting energy from nuclear sources, or who knows, maybe physics we don't understand, you still have to dump the energy when you're done with it. So large panels for doing radiating might be a universal feature of any energy-hungry species.
And it may simply be that if you do detect a technosignature, it may not be saying hello at all. Rather, it's just simply doing its thing, radiating out heat.
That's right. And that was one of the things that Freeman Dyson was getting at with his paper, was that it seemed to him that the radio approach described by Cocconi and Morrison in 1959, and that Frank Drake pursued with Project Ozma, relied on a lot of intentionality on the part of the transmitter. It assumed, well, it didn't assume, but it works best if someone's trying to get our attention and doing something very obvious and obviously artificial. I think what Dyson liked about his idea is that it didn't assume that at all. It simply assumed that they used energy, which seems like a much more natural and generic assumption. And so didn't require us to do any xenopsychology, basically, about what they might be up to or why.
I read on your blog you had lunch with Freeman Dyson, didn't you?
I did. We ate at Burger King.
Burger King, huh? Well, Burger King's good, though.
It was good. He had a hot dog.
Okay, so how do we look for Dyson Spheres outside of, say, just a shell where we're just looking at infrared? Say we're looking for stars with weird luminosity, weirdly low luminosity. How do you go about doing that? How do we look for this technosignature? Yeah,
it depends on what it is that you think you're looking for. So if all you're after is there a lot of industry around the star, then all you need to look for is what Dyson suggested, which is excess heat, excess infrared radiation. So that's challenging from the ground because heat's all around us. Everything gives off heat, including the atmosphere. And so trying to look through Earth's warm atmosphere at infrared, mid-infrared radiation is very challenging. But if you go above the atmosphere, when you put a satellite in space, an infrared satellite, then you can look to see what the sources of infrared radiation are. And that's what happened in 1984 when NASA launched the infrared astronomy satellite IRAS, and discovered that there are a lot of things out there that give off infrared radiation, way more than anyone had anticipated. And so that was great for infrared astronomy, but it also meant that it was going to be harder than people thought to look for Dyson spheres. Another way you can do it, like you said, is looking for stars that seem to have light blocked for some reason. So one way, as you say, is just to look for stars that seem too dim, maybe because they're embedded in a large swarm of material that's blocking a lot of the light. And you can do that. The problem is that some stars are just dim. We have subdwarf stars that are just dimmer than they should be. Also, you, until recently, didn't really know which stars, how far away they were, so you didn't know how bright they were supposed to be. So it was hard to tell that they were dim. Today we can do that a little bit better. But it takes a lot of material to make a star so much dimmer than it's supposed to be that you would necessarily notice. So I think the infrared approach is superior there. The last thing you can do is follow Luke Arnold's suggestion and look for traces of large things going in front of the star that can't possibly be planets. And so here you're looking for stars that just are going along at their normal brightness and then suddenly get dimmer in ways that you can't explain by another star or planet orbiting it. And there should not be very many of those because there's not a lot of stuff around most stars other than stars and planets. So that's been the idea of using the Kepler data, later K2 data, and now TESS data to look for stars with anomalous dimming patterns characteristic of material that might be orbiting them that shouldn't be there naturally.
Let's go into the utility of a Dyson Sphere, in whatever form it is, Dyson Swarm. Now, what could you do with if you were harnessing that much energy?
Yeah.
What would you do with it? I mean, would you try to store it? And I know in your paper you mentioned the possibility of converting it to antimatter.
Right. So technology, you might define it as the application of the intelligent application of energy. So if you're going to use technology, it does something with energy in some way. What do we use our technology for? We use it to move stuff around and overcome friction and build things and destroy things and go about moving and living our lives. So it could just be all of that. We use it to do, chemistry to smelt things and create new materials. They could use it for that. More and more, we're using it for computation. A larger and larger fraction of all of humanity's energy use is going to shoving electrons through silicon. And that's another thing that you might do with a Dyson Sphere. You could do enormous numbers of computations. And we are finding as we enter the digital age that that's a really useful and interesting thing to do with your energy. The one thing you can't do is keep it, with the one caveat that you mentioned. The amount of energy that the sun puts out is enough to take Jupiter and completely deconstruct it down to its individual atoms and scatter them far, far away in thousands of years. And so it's just such an enormous amount of energy. There's nothing you can do with it that results in that energy staying in the system. And so that's how we know they have to get rid of it at some point in the form of infrared radiation, and why we should be able to see that infrared radiation come off. Now, your other two options are you could radiate it away not as heat, but as, say, radio waves or lasers or something like that. So you could create very powerful transmissions, and of course that's what we hope they're spending some of their energy doing when we look for laser signals or radio signals from space. The one caveat is that you can keep it if you convert it back into mass. Remember that starlight was mass. It was hydrogen when it was in the core of the star. Fusion in the core resulted in the release of gamma rays that come out of the surface as ordinary light, which you could then capture. And in principle, you could put it back together into matter. Now, why would you want to make hydrogen out of it? That would be kind of silly. You've got a gigantic ball of hydrogen sitting right there called the star. To convert its light into hydrogen is extraordinarily inefficient compared to just picking some up off the surface. But you could also create antimatter with it. And that's interesting because antimatter is just not around in very much abundance. And so in principle, I don't know how you would do it, but in principle, you could use the energy to make antimatter. And that would allow you to keep in the system I don't know what fraction, a significant fraction of the energy coming out. So those are the broad categories. You can radiate the energy away as a signal of some kind. You can radiate it away as heat. You can make matter or antimatter with it, or you can do all the things we do with it, such as computations and so on.
The one difference there, though, I think, is that if you're radiating it out as heat or radio waves, everyone's going to see that.
Right.
But if you're creating antimatter, that might not be so visible, right?
No, that's right. And of course, if you send out a very well collimated beam of energy, then most directions will not see that either. You could also imagine trying to convert it into, say, neutrinos or something, which are very difficult to detect. Or gravitational waves, perhaps, which are also very difficult to detect. So there are ways to send it out, but there's also a fundamental limit to how much of the energy you can put into stuff other than heat. It's called the Carnot efficiency. And if the work you're doing around the sun is like you would do it out here, so the way to think of the efficiency, is how close you are to the star when you do the work. Because that tells you the typical temperature of the thing doing the work and the heat that you radiate away. So for the sun, the surface is about 6,000 Kelvin, 5,800 Kelvin, something like that. And so the radiation is high temperature or low entropy, we say. By the time it gets out to Earth, we can take that wonderful low entropy energy, we can collect it with solar panels, we can do all of our stuff, and then when we get rid of it at a low temperature, at 300 Kelvin. And the efficiency with which you can run that engine of collecting starlight and then giving off the heat at 300 Kelvin is about 95%. So in principle, we only have to radiate away 95% of the sunlight that we collect, and that's true whatever. The only problem is if you keep too much of it, like, it's just too much. So unless you're making antimatter or beaming it away, you have to get rid of it. So you can work about 95% efficiency if all this stuff is about 1 astronomical unit, the Earth's sun distance from the star. If you want to go to 99% efficiency, so you want to collect the energy and use it in a way that's not noticeable and only give off 1% of it as heat, then you need to go out much farther. You need to go out to 10 AU, I guess. And that requires much more material because a sphere that's 10 times as big has 100 times the surface area. And so the more efficient you want to be, the farther out you have to build, which means the more material you have, and you quickly get diminishing returns. So it seems to me unlikely that you'd be able to work with so much material at such a huge distance that you would be so efficient at using the energy that you would not be noticeable in the infrared.
Now, it could be said that we as humans, with our solar orbiting spacecraft, have begun to build a very, very rudimentary Dyson Swarm.
Mm-hmm.
And that would say that the sun is a pretty good star to do this with. Now, other stars. Are there stars? I mean, you obviously wouldn't want to build a Dyson Sphere around a star that's about to supernova, or one of those gigantic stars that
Mm-hmm.
you don't live on.
Short-lived, right?
But in the Type K and Type M red dwarfs, are those better stars for Dyson Spheres than something like the Sun or a Type F star?
No, because they are dimmer and they have lower temperature radiation, and so there's just not as much work you can extract. So if you're looking for a nearby star to build a Dyson Sphere around, you're much better off around the brighter star, the hotter star, just because it's got more energy for you to use. And if you're building a Dyson Sphere, I'm assuming you need some enormous amount of energy to do what you like. So we say that these are short-lived stars, but a star like the Sun still lasts 10 billion years. And even an F star that's a little hotter and a little brighter, but has a lot more energy to give, will still last billions of years. And so I'm not sure that, that's too short to be worth it. I mean, the energy is there to take. You can have it for 1 billion years or maybe even only 100 million years, so why not take it? So I don't see why they wouldn't build Dyson Spheres around the most energetic stars.
What about other weird stuff like a neutron star or maybe even a black hole? Is there any reason to build a sphere around that kind of stuff?
Yeah, people have thought about this. I don't see great value around, say, neutron stars. Now, some of them have very strong magnetic fields like pulsars, and there might be some value there, but there's just a lot more energy to be had around an ordinary star. Now, a black hole is interesting because unless it's busy accreting something, stuff is falling into it, it's not giving off any radiation at all. But people have argued that it's a very interesting place to be because you can extract energy from it. And there's also some interesting things you can do in terms of entropy with computation if you can access the hole. So there are curious things you can do if you're near a black hole. So you might see something there. But black holes generally don't have a lot of luminosity, so there's nothing we could do to tell that they were around the black hole. The black hole's hard enough to see as it is.
Looking for Dyson Spheres or Dyson Swarms. I remember years and years ago, a scientist, and his name escapes me now, actually did a rudimentary search and came up with a few candidates. Weren't very good ones, but came up with a few candidates. And then I think it was you, wasn't it, that looked at galaxies, trying to see if anybody had encased most of the stars of a galaxy in Dyson Spheres. Mm-hmm. Did you find anything? Did you find anything interesting that might...
We found lots of interesting things. No Dyson Spheres, but yeah. So you're thinking of Dick Kerrigan's work at Fermilab.
That's correct.
So I said that in 1984, the IRAS was launched, and it was going to be very hard to find a Dyson Sphere in that data set. But Dick worked on it for a long time and years as a hobby, basically. And eventually, as you say, he published a upper limit on the whole sky that he hadn't seen any. But he did list some candidates that are almost certainly a particular kind of giant star at very large distances. And actually, someone should go check now that we have distances to those stars and confirm that that's true. It's on my list of projects to do one of these days. And then, we did a similar thing. And the first thing we wanted to do was a more sensitive version of that search using a different satellite called WISE that NASA launched, the Wide Field Infrared Survey Explorer, I think. The problem was that it was too good, that it found 100 million sources of infrared radiation in the sky. Almost all of them are distant galaxies. And that was just too big a haystack to go crawling through, especially because we knew that we would soon have distances to them all from this additional satellite that went up called Gaia just a few years ago. So we punted on that and said, well, wait till we have distances and we know which ones are stars and which ones are galaxies. For now, let's just look at the nearby galaxies, because the argument goes, if a species can build a Dyson sphere, they almost certainly can travel to other stars, because it's easier to build a Dyson sphere than it is to travel, it's easier to travel to another star than to build a Dyson sphere. And so if this is a thing that a species does, they, might not only do it once, they might do it across the entire galaxy. And so if Dyson spheres are a common byproduct of technology, we would actually expect to see many of them in a given galaxy. And so I was curious if there were any galaxies out there that just had way too much infrared excess heat coming off of them for their type. And so that's what we did. We looked at all the nearby galaxies because we knew how far away those are. We looked at 100,000 of them, and we found lots of interesting stuff. We found a few that definitely had too much excess heat. They are presumably what we call starburst galaxies. They just have a huge amount of star formation and dust going on. It's a common galaxy type. But what we did show is that there aren't any galaxies out there with something like half of the starlight being processed into Dyson spheres. And that's, we basically knew that ahead of time, or at least we could have guessed that. But we didn't know that. Until WISE went up, we didn't know if there were any galaxies like that, and now we do. And that's how science progresses. You start by not knowing anything, and then you do some rough work, and you know a little bit more. And I'm confident that if we ever get funding to pick up the project again, we can do much better than that. And in particular galaxies, I think we could show if even 1% of the energy of the starlight were being used by Dyson spheres.
Now, you mentioned that the instrument was producing more results than you could analyze. How about automation of that? I mean, can you write a program that picks out the most interesting light curves from these instruments?
Sure. That would be something you would do to look for the material passing between us and the star, for instance, with the Kepler dataset. So NASA did this, but of course, when NASA launched the Kepler Observatory, it was thinking about finding planets, not Dyson spheres. And so they had a data processing pipeline that went and looked for planets, and it would classify things through various algorithms as being a planet candidate or not. And that meant it missed a lot of really interesting things. And so people have thought about what to do about all the missing interesting stuff, including the missing planets. And so there has been work by a lot of people to try and build better classifiers that are better at finding planets or good at finding anomalies. But the first one that was really successful was the Planet Hunters project, which didn't use any automation at all. It crowdsourced the problem and just asked citizen scientists to by eye go looking through all of the Kepler data for the planets that had been missed. And that's how a lot of really interesting anomalies in the Kepler set were found.
Now, there is one particularly interesting one that I would be remiss without mentioning. KIC 8462852, or Boyajian star.
Yes.
Now, this was, for a time, a really interesting star in regards to the possibilities of Dyson spheres. And it continues to be interesting.
It is still an interesting star, but not for Dyson spheres.
Yes. Now, what knocked it out of the running was that it is not opaque. It didn't block all of the light from the star. It just blocked some of it, which screams dust.
Right.
But it's just dust in some weird juxtaposition around the star. Any ideas or anything new on just what that dust could be doing?
No, I don't have anything new. You're right. I worked with Tabby Boyajian and an astronomer at Arizona State University, Eva Bodman, And we studied the star to try and figure out what was causing it to get dim. And it was getting dim in a way that, was very reminiscent of Luke Arnold's paper and Freeman Dyson's, light through the chinks in the armor ideas. And as you say, we noticed that when it got dimmer, it got much dimmer at blue wavelengths than at red wavelengths. And that just screams ordinary astrophysical dust. And dust exists around stars. Normally, that wouldn't be so surprising, but this is not a young star that should have much dust around it. I think we still don't have a good model for exactly what's going on there. The best model right now is Tabby's idea of Exo Comets, so gigantic, scaled-up versions of the solar system's comets, just enormous ice balls that will occasionally come in and sublimate huge amounts of material that condenses into dust, and it gives off all this dust. And that's what these dips are, these gigantic comets going in front of the star. That's still, I think, the best idea, but I think we still haven't ruled out a lot of alternative explanations. I mean, the dust could be in the interstellar medium between us and the star in very strange configurations. We wouldn't really know, except that it would occasionally make a star do something like that.
There was an interesting feature in the light curve, I think day 792 or something like that.
Yep.
That was a very, very smooth curve that, ingress and egress out. And I guess one way you could interpret it is that it's an isosceles triangle, which one thinks comet, right?
Yeah.
But it was pointing in the wrong direction, as I recall. the tail is like.
I guess that's true. You'd have to have the thin fat, or it's sort of in the wrong direction, I guess. I'm not sure that's such a problem because comet tails can point in funny directions and do funny things depending on what they're made of. But yeah, that one, whatever blocked the light blocked something like 20% or 15% of the starlight. And that's just an enormous amount of dust to in one direction block so much of the energy of the star. It's practically opaque at that point. Not completely opaque as we found, but it's still I'm still really challenged by this star. But we did what we could to try and figure out what it was. We took spectra during the dips and we didn't see anything, so I'm not really sure what that means. It's
strange. And then what about this weird lack of infrared?
Yeah, exactly. If it's dust around the star, just like a Dyson sphere, it should warm up. And every time a dip happened, they pointed Spitzer's space telescope at it, and we never saw any excess infrared emissions. So hopefully we'll be able to point the James Webb Space Telescope at it, catch it during one of these dips, and see that infrared excess. And if we don't, then I think that means that this dust isn't actually orbiting the star, that it's between us and the star. And I think that's really interesting too. That's my dark horse candidate for what it could be, that it's something in the interstellar medium.
Interstellar medium, yeah.
I actually like the idea that it's a ring of dust around a black hole, because there should be all these stellar mass black holes in the galaxy. There's no way to see them because nothing's falling into them. But they should have these gigantic rings of cold material. And if one of those ring systems passed in front of a star, it would look an awful lot like Tabby's star. So that's my favorite idea. It's unlikely, but I think it would be pretty cool.
That would actually, I would rate that as cooler than finding an alien Dyson sphere. Because
I think the Dyson sphere is way cooler to find. But yeah, I think that would be a lot of fun.
Now, what about intrinsic variability with the star itself? Could it be just the star forming huge sunspots or something like that that's giving the appearance?
Could. The fact that when it gets dim, it gets red is really consistent with dust, but it's not totally inconsistent with the idea that there's something on the surface of the star, like a cool spot or something like that. So that's I think still possible, but I think it's pretty unlikely. The main issue is just that we think we see the rotation period of the star, and it's consistent with what we expect the rotation period to be. But if the cold spot were on the surface, it should be modulated by the rotation period of the star. And as you said, the day 792 dip is very smooth. It lasts weeks, and so there's no reason that a spot would evolve so slowly if it's supposed to be spinning around every time the star goes around. Now, it's possible the entire star, for whatever reason, got dimmer and cooler. There is someone pushing that idea as well. But again, we don't have any precedent for that. Other stars don't do that. We don't know why a star would do that. So to me, that lacks physical motivation.
Now, the star has been monitored for several years, since crowdfunding. effort to monitor it. Has the star produced any dips similar to Day 792, or has it just been more similar to the rest of the dips in this star?
More similar to the rest of the dips. I mean, it's hard from the ground to see all of the bumps and wiggles that Kepler was able to see, but there have been a couple really good ones that were a few percent, and those are the ones that we use to determine that it's dust causing the dips.
Now, is an astrobiological explanation for Boyajian stars still on the table, or is that just dead?
I don't think there's any reason to suspect a technological origin to the dips any longer. The fact that it's consistent with dust and not consistent with an opaque object with sharp edges, I think that basically rules out, well, it doesn't rule out technology, of course. You can never rule out technology, but it removes any motivation to pursue that hypothesis.
This dust has to be very, very small. It's more like cigarette smoke than dust.
Oh, even finer than cigarette smoke. Yeah, that's right.
Now, is that unusual? I mean,
no, that's very common for astrophysical dust. I mean, we call it dust, but as you say, it's not like, the dust that accumulates on your bureau or something like that. It's made of a lot of stuff, but it's just all the little bits of stuff that's out there in space, from stars that explode, from stars that have winds that blow their material away. All of that stuff hanging out in space, a lot of it is atomic or just molecules, but when it gets cold enough, those molecules will start to form very small grains. And very small, we're talking, microns or something like that. And when you have dust that small, it will preferentially block short wavelength light that's shorter than it is large, and let longer wavelength light, longer than it is large, through much more easily. And so that's how we can distinguish it.
Is there any way to determine the composition of the dust? Or is that just not possible at a distance?
In principle, you can. It's challenging. If the dust were shining and glowing, then yes. So if with the James Webb Space Telescope we can pick up that emission, it's possible we might be able to make some inferences about the dust's composition. And in absorption, if the dust is close to the star and some of it is hot, and in gaseous form, we might be able to pick stuff up that way as well. Although we did try that and we didn't see anything. But if it's dust, we basically know what it is. Most of the dust in the universe is made of similar stuff.
Yes, and well, actually, we have a visitor right now, Comet Borisov, that appears to be exactly the same as a solar system comet, suggesting, of course, that everything is made out of the same stuff. Now,
except for Oumuamua.
Well, Oumuamua, but that's a mystery. I'm not sure I want to. I mean, I've interviewed people regarding.
That's fine.
But actually, what's interesting me the most about Oumuamua lately is this idea of the hydrogen iceberg.
Yeah, that was interesting. I think Avi Loeb had a response to that it doesn't work for some reason, but I admit I haven't followed it very closely.
I haven't followed it either, but I was interested in that because if you have an object from a star-forming region, a failed star-forming region, passing through the solar system, that seems to me something that we got to prioritize as far as studying.
Yeah.
We got to get a sample of that, if such things exist. But I think now with the Vera Rubin telescope coming online, we're going to see a lot of interstellar objects, and I'm
very excited about that. Yeah, and I know there are a lot of plans on how we'll follow them up. That was the really great thing about Oumuamua, that it was a dry run, and it's unlikely that the very first example of an object that you find will be, the last time you see that kind of object. And so it's very likely we will see other things much like Oumuamua coming through, probably in great numbers, as you say, once the Rubin telescope is operating with the LSST. And that'll be really neat. And hopefully it's not out of the question that we could even visit one with a spacecraft. You can't really catch these things and catch up to them, but you can get in their way and catch them as they zip by really fast and even potentially get some samples from them.
I think the scary thing for me in that whole thing is what happens after 20 or 30 years of looking at interstellar objects. We have never seen anything remotely close to Oumuamua. They're all Comet Borisovs.
Yeah, I mean that's possible. There are plenty of examples of it taking a very long time to find another example of the first one that you saw. So the first Dave Latham's what until recently we thought was one of the first planets ever found. In 1989, it was the very first star they looked at with precise radial velocities, and they discovered this object. And then everything else in their sample, they found nothing. And similarly with brown dwarfs, the very first object they looked at with the new Keck telescope coronagraph, they found what would turn out to be a brown dwarf, but then nothing else in their sample had it. And so it took a long time before you got the other one. So it's possible, but I'm sure eventually we'll see another Oumuamua-like object.
Now, this also applies to Boyajian's star, because now we're starting to see things that look a little bit like it.
Yeah.
So
it's hard without the precision of Kepler, but that's right. There are some ground-based surveys that have started to find other examples of things like Boyajian's star. It's hard to know how like Boyajian's star because they've generally been fainter and they've generally been farther away, and we don't have quite the precision on them. We don't have just that exquisite photometry that Kepler gave us. We don't know enough about them to really know how weird it is. I mean, something people forget about Tabby's work on that star was that it's not as if the citizen scientists spotted this thing and she said, wow, that's weird, and published. She worked on it for 2 years to try and figure out what it was and proving it was anomalous before she finally published. She was very reluctant to publish until she had solved the mystery, actually. So, yeah, we have these other things that might be in the same category, but until someone of Tabby's caliber works on it for 2 years and proves that it's really anomalous, we can't really be sure.
now, one thing about that particular star is it also had another feature that seemed apparent, and that was a long-term dimming over the course of decades.
Yeah.
Do you still see that in the data that's coming in?
Oh, that's very hard to tell. I mean, yeah, it seems to be slowly getting dimmer over a long amount of time. And that was first pointed out by Bradley Schaefer, who went back to the plates and showed that over 100 years it seems to have gotten dimmer. That's very hard work to do, to properly interpret photometry on these 100-year-old photographic plates. Bradley was one of the only astronomers in the world that you can really trust to get it right, which makes it very hard to check and confirm. And then Kepler also saw that it was getting steadily dimmer just over the few years that Kepler observed it, which is amazing. I mean, it was a much more rapid decline than Bradley had detected. But again, it's going to be very hard to confirm that from the ground without either a huge, 100-year baseline or extremely precise photometry of the sort you only get from space. So I would love to see if these other stars have similar changes in brightness over long periods of time, but we just don't have a way to measure that right now.
Now, Kepler, which is now gone. At the time, I wish we were manufacturing Kepler spacecraft and pointing them in all directions because we saw so many amazing, I mean, how many exoplanets did that thing
Yeah,
show?
the thousands and thousands.
Yes, so it's Kepler, to me, it was probably the most successful photometer in history. Now,
No, that's right. But remember, it also, I mean, it cost $500 million. So we got our money's worth.
yes. But now we have something else. We have TESS. Is TESS a good replacement for Kepler, or is it just not quite in the same league, or are they just two completely separate instruments that do two different things?
Right. It's a little bit of both. So TESS is $200 million. So right away, you know that it's not quite as sophisticated or not. I'm sorry, not as sophisticated. That's not the right word. But right away, you know that it's cheaper and therefore probably not quite the same in terms of what it can do. It's different in that Kepler stared at one patch of the sky for its prime mission and got us years of data on about 100,000 stars. TESS is going to give us more like a month or two of data on most of the sky. So there's only a few parts of the sky where TESS will stare almost continuously for years, and TESS also generally looks at much brighter stars. So this gives us a different parameter space. We're looking at stars that are easier to study because they're closer and they're brighter, but we're not looking at them with the same photometric precision that Kepler had, and we're not looking at them for as long as Kepler did. So we're going to find closer in planets. And we won't be able to get planets that are quite as small, but we'll look at so many more stars that we'll get much better statistics in a lot of ways. So it's better in some ways and worse in others.
I'm not to go all Douglas Adams on you, but I'm envisioning a civilization that builds millions upon millions of Kepler spacecraft, and it becomes their Dyson Swarm.
Right, exactly. And yeah, you said before that we've sort of started to build our Dyson Sphere, and that's true. We have solar panels in space, and one of the things I think about in terms of Dyson Spheres is that you mentioned at the top about the canard of a monolithic shell, just one single structure. And something that like that requires, well, first of all, it's mechanically impossible. No material is strong enough to be able to hold itself up against the star's gravity if it were a single solid object. It's also dynamically unstable, and it would drift into the star. I mean, there's all sorts of difficulties with that idea, unless you're invoking, basically magic or something like that. And there's no reason to do it besides, because everything you would want from a Dyson Sphere you can get just as easily from a swarm. But the nice thing about the swarm idea is that it doesn't require this really intentional feat of engineering, right? I think about our megastructures, like, say, New York City, right? New York City is a megastructure. It's just this huge interconnected web of concrete and steel and wood and electricity and people and subways and everything. And it's all connected in this gigantic object. But when they first started planning New York, that was not the plan, right? It was incremental, that every few years they're like, well, we'll make it a little bigger. We'll make it a little bigger. And with a swarm, that's what you can do. You just say, well, we just need a little more energy. Put up some more solar panels. Put up some more solar panels. And so it removes that xenopsychology of, well, this is how they would go about solving the problem. It could just be the sort of thing that naturally happens.
Practicality. And one would imagine that if you're an alien civilization that's going into space, you understand what practicality and reality is.
Well, I try to, humanity does a lot of really big projects, like building its cities and altering our atmosphere. And not all of the projects we do are all that intentional. Some of them are just pure byproducts. And some of us disagree about doing those things. We have a lot of different opinions about how to do all of the things that we do and whether we should do them and how to do them. And there's stuff that we're doing that we don't even know we're doing. And so when I try to think about the problem of alien technology, I try to avoid thinking, oh, they would do X. Because if you look at human psychology and say humans would do X, you miss a lot of the things humans do, because a lot of the stuff we do isn't innate to our individual psychologies. It just sort of emerges out of our coordination or our lack thereof.
My one final question about Dyson Spheres is that looking for technosignatures is now back on NASA's plate for the first time in decades. What are you guys going to do with that?
I know. Yeah, that's right. It's back. NASA's seriously considering funding it. And in fact, they have. We just announced this week that the University of Rochester has won an award, a grant from NASA, competitive grant from NASA out of its exobiology program to think about atmospheric technosignatures. So in this project, what we're going to do, I'm a co-investigator on the grant, is we know that we're going to be probing the atmospheres of exoplanets to determine what they're made of. So especially rocky exoplanets that we think might have liquid water on the surface. And NASA is very clear that, we're after biosignatures here. We're trying to find the traces of metabolism in the atmospheres of these planets so that we can determine if there's life elsewhere in the universe. But, if you were looking at Earth's atmosphere, in addition to seeing our biosignatures, the methane and ozone in our atmosphere simultaneously, for instance, you might also be able to detect our technosignatures. We have chlorofluorocarbons in our atmosphere that are very distinct. We have NOxes, we have these nitrous oxides in our atmosphere, and a lot of that is biogenic, but a lot of that also comes from combustion. And so that's another technosignature. And so this grant, we're going to add technosignatures to the list of things to check for when we get these spectra, atmospheric spectra of these other planets. Just so that when NASA's doing its astrobiology and looking for those biosignatures, they don't stumble across a technosignature and miss it and say, well, we don't know, it's not methane, we don't care. We'll say, wait, that's a chlorofluorocarbon. Like, that has to be artificial. You've actually found life.
What's the possum doing? He looks very focused.
He's counting down before mission launch, John.
I see. What? Mission launch?
Since you mentioned the possibility of a more efficient computing cloud, I redirected some funds to investigate it as a possible enterprise.
Redirected what funds? You better not be spending my beard money again. I am not going back to beeswax. There were bees in it.
Your beard maintenance budget accounts for 78% of our expenditure now that we no longer have a car.
Wow, you weren't kidding. That thing's like a real rocket. How'd you get a permit for that?
Best not to ask questions.